Okay, I'm sorry, Sasha, darling, but you. Okay. All right. Ow. Okay, getting used to the new desk. Okay. What the hell happened here? Let's go ahead and edit that. Did the camera move? No. Maybe it did. Yes, it did. I bumped the desk. Okay. Okay, let's fix this wire. It's annoying. Alright. That'll do for the moment. Now let's get the camera better. Alright, okay. Alright. Alright, so Chapter 2, Light and the Death of a Science. I might be being a little bit melodramatic there. Don't think I am, but you never know. Okay, so, light. What is light? Okay, so, when I talk about the death of a science, I'm talking about the end of the 19th century, the beginning of the 20th century. Discoveries were piling up, okay? Basically, the way they were working with physics. Okay, they were just they just kept on working, and the way it was, what was happening was basically they were coming into more and more information that was showing them that their understanding of physics was not going to work. It was not good enough. So we're talking about the transition from classical mechanics of the 19th century to quantum mechanics of the 20th century. Okay? To quote the comedian, "Science knows it doesn't know everything, or it would stop." Okay? Under classical mechanics, the world is made of atoms and it runs like a clock. It is very mechanistic. If you have enough information, you can predict everything. Okay? People thought, they honestly, literally thought that science was coming to an end. That they were putting the closing notes, the finishing touches on science, and that soon they would be done. Okay, they were wrong about that. So one of the things that was coming to an end, that was really piling up the contradictions, I should say, was their understanding of waves. Okay. So waves, they analogized them from ocean waves, where the wave is energy traveling through the water, and you can see that energy traveling through the water thanks to the displacement of the water. The energy causes the water to both lift up in a peak and push down in a trough, either in front of or behind, in the front of or in the back of the wave. Okay. Oops. So that was how they understood waves, was by recognizing them from the ocean. And they knew that light behaved like a wave because it had the various behaviors that both ocean waves and also sound waves display. So first off, here in this upper left-hand corner, you have interference. Here we have two waves. There, the peaks line up and the troughs line up. Okay, that's known as constructive interference. Waves, when they pass through the same space, will add together. If you get positive with positive, you get more positive. Negative to negative gets more negative. That's known as constructive interference. But if they don't line up that way, if positive adds to negative and negative adds to positive, then you get destructive interference, and it cancels out. Okay? So you see this with ocean waves, you see this with sound waves, you see this with light waves. In sound waves, that is the principle behind noise-canceling headphones. they have software built in that analyzes the sound coming in from outside and immediately produces sound waves to cancel them out. Destructive interference. It's not perfect, it can't be, but it works pretty darn well. You also get down here diffraction. When a wave enters a new medium or a medium with a different density or just slightly different properties, if it happens at an angle like this, then the wave will bend. It will travel in a new direction. In the case of ocean waves, you see this happening as the wave moves from deeper, denser water into shallower, less dense water. You also get diffraction around corners. Okay, waves don't end; they don't terminate. When they're traveling along, you do not see this. Let me bring up my paper. Okay, you don't get something like this. Okay, here's the corner. Here's the wave moving along. And it doesn't just keep going and suddenly cut off right there. Instead, it will wrap around the corner. Okay? It will bend. That's why you can hear someone around a corner. That's why you can see light coming around a corner. It gets weaker when it does that. It takes more energy. The wave gets more diffuse, more spread out. But that is what allows you to see and hear things. So that is what we're seeing here in the upper right-hand corner. That is also what's happening down here in the lower right, okay? Where instead of moving around a corner, essentially it's moving around two corners. The waves are moving forward, they move through a gap, and because they don't like to end, instead you get these concentric circles kind of coming out from that gap. So those are different things that you see with waves. You see them with ocean waves. If you had a barrier set up in a swimming pool and you sent waves at it, this is exactly what you would see. And they also happen with light waves. Okay. Now, when things get interesting is when you combine this stuff by having not just one gap, but two gaps. So this is something that you can actually see. You send light, you just shine a light on a barrier with two slits cut in it. Okay, you can just take a piece of cardboard, carve two narrow gaps in it, very narrow, with a knife. Just basically stab it with a knife twice. And you'll get these two sets of concentric circles coming out from each of those gaps. Now, when that happens, you'll have two sets of waves, and thus you'll get interference. Where peak overlines with peak, you get constructive interference. The light gets very bright. Where peak overlaps with trough, like right here, you're going to get destructive interference, and it's going to get dark. Where trough overlaps with trough, like right here in the middle, this white space, you're going to get, again, constructive interference, and the light is going to be very bright. Okay, no comments yet in the chat. Good. All right. And what that produces is what's known as an interference pattern. So on the far wall, you shine the light from the left, you have the barrier with two gaps in the middle, and then you have a wall on the far side. You get this interference pattern, this alternating set of bands, light and dark, constructive interference, destructive interference. Again, you could do this with a swimming pool. You have a swimming pool, you start sending waves out from one side, you have a barrier with two gaps in the middle. On the far wall, you would get an interference pattern. Only instead of light and dark, you would have places where the water's going way up and down, equivalent to the light bands, and places where the water's not moving at all, the dark bands. Okay. So that is an interference pattern. So that is one of the ways, again, that they knew that light is a wave, because it produces this interference pattern, constructive, destructive interference. And here's a photograph of exactly that. You have the light shining in from the bottom. Here you have a gap. Over here, kind of covered up by the thing, you have another gap. And then you see these bands of concentric circles shining onto the floor. And then you can see where they start interfering with each other, you get dark and light, dark and light. So within, the place where this wave is dominant, just because of how bright it is, you start to see these striations. And in the middle, where they're equal, you can see that they, cancel each other out more perfectly. So they knew that light was a wave. And under classical understanding, they said, okay, light is a wave just like an ocean wave. And here are the factors that they used to understand, to describe and define waves in the ocean. Amplitude, that's the height of the wave. That, in the case of the ocean wave, that's literally how high the wave is, how far it displaces the water from the level. Water wants to lie flat. You have to put energy in to lift it up. You also have to put energy in to push it down. It doesn't want either one of those. It wants to lie flat and even. So the higher the wave, that's how much energy you put into the wave. Then you have frequency, wavelength, and speed. These three are kind of connected to one another. They're not fully independent. Frequency is how often a peak or a trough, one or the other, how often it passes a location. So the unit for frequency is the hertz, or 1 per second, or inverse seconds. So peak or trough, that doesn't actually have a unit, so we leave that part blank, but it would be peaks per second or troughs per second. It's actually named after a German physicist named Hertz, but it's entirely appropriate because Hertz is also the German word for heart. So lub-dub. Very nice, gives you a decent frequency. Wavelength is also the distance between peaks and troughs, but instead of the distance in time, we're talking about the distance in space. So that's literally just measured in distance. And then we have speed, which is how fast the wave is traveling through the medium in question. So how fast does the wave travel through the ocean? And speed is equal to wavelength times frequency. Meters times 1/seconds gets you meters per second speed. So these three are sort of connected to one another. So light does all of these things, but it's also different. Light has an amplitude in that's just the brightness of the light. A dim light has a very low amplitude. A very bright light has a very high amplitude. Frequency and wavelength are a little bit more complicated, but they're essentially related to the color of the light. Light has a spectrum going from red to blue, where red is a very long wavelength, a very low frequency light, and blue is a very short wavelength, a very high frequency light. Okay? And it all travels at the same speed. Now, the thing is, by the end of the 19th century, early 20th century, we see that a lot of experiments are starting to show that light doesn't behave in the same way as an ocean wave. And these differences are building up, and it's causing a lot of problems. Okay, first off, we have Michelson-Morley in 1887. They were studying what's known as the luminiferous ether. They showed that light doesn't have a medium. Then a guy named Rydberg made some observations about absorption and emission spectra. Then we have Max Planck solving the problem of black-body radiation. And then we have Albert Einstein solving the problem of the photoelectric effect. So let's go into these in more detail. Okay. So here is, we're going to go into those in more detail, I should say, in the next slide, next set of slides. Okay, so here is the electromagnetic spectrum. When I saw that it was available in German, I jumped on it because I had just started studying German, so it was fun. So up at the top, we have wavelengths measured in centimeters. Doesn't really matter. It can be meters, could be centimeters, micrometers, whatever. Electromagnetic spectrum includes light, right here in the middle, the visible spectrum, but that's just a very small section of light. On the far side of red, you have infrared, or infrarot, if you're speaking the German, which comes in far, middle, and near infrared. And then just beyond that, you have microwaves, so called because the wavelengths of microwaves are in micrometers, microns, micrometers. Then beyond that, you get into radar. Radar waves, you're starting to get into the centimeter region. So they're starting to be at about the same size as physical objects. Then TV and radio waves, beyond that, you're getting into meters and then tens of meters or even kilometers. Going in the other direction, on the far side of blue, you have ultraviolet, which is just near and far ultraviolet. And then you have various kinds of, then you have X-rays on the far side of that, and yes, those are the X-rays they use in hospitals. And then beyond that, you get into gamma radiation. No, that will not turn you into the Incredible Hulk. It will just give you cancer. So here in the middle, we have visible light going from red, starting, if depending on how good your eyes are, 800 to 700 nanometers, then orange, then yellow, then green, then blue, then violet. For those of you who memorized Roy G. Biv, like I did back in the day, the Germans don't have indigo. That's because indigo was thrown in there by, what's his name? Sir Isaac Newton. Isaac Newton, the guy who developed the laws of motion, who solved the problem of the motion of the planets, incredibly famous physicist. He came up with classical mechanics. He was the word in physics for about 200 years there. He considered that his third most important contribution to science. His second most important contribution was actually his work on alchemy. In addition to being a genius physicist, he was also an alchemist. They went ahead and opened up his tomb, took a sample of his hair, and found that it was loaded with mercury. The dude was nutso for alchemy. And no, nobody remembers his contributions in alchemy because alchemy is bullcrap. Next up, his most important, the number one, the thing he thought would truly stand the test of time, was his work on Bible codes. So yeah, we're talking the Da Vinci Code, Dan Brown, the stupid nonsense that crazy people believe that you can use to tell the future by picking letters more or less at random from the Bible. Yeah, that was also Isaac Newton. And no, that did not stand the test of time. But the reason he put indigo in between blue and violet was because he thought that 7 was a magic number, and he wanted there to be 7 colors. So he just, indigo, blue, indigo, and violet. And the Germans, because they do not care about Sir Isaac Newton, I'm imitating my father's friend Otto with this German accent. They didn't care about Isaac Newton. They didn't care as much about the number 7. They just looked at the colors that are actually there. So red, orange, yellow, green, blue, and violet. All right. So that is the electromagnetic spectrum from radio waves out to gamma radiation at the far end, with visible light just about at the middle, insofar as an infinite spectrum can have a middle. And that is it for this particular set of slides. I'll be back in about 2 minutes to continue with Chapter 2, talking about Michelson, Morley, and the Rydberg experiments. That'll be the 8th set of slides. So Chapter 2, point 8, Michelson, Morley, and